that is electrostatic. Last class we discussed a lot about what is electrostatics and the properties of the charges. And after studying the properties of the charges, we have moved to the properties of more the physics behind the two charged bodies, and so that is described by Coulomb's law. And we also have seen how this Coulomb's law was developed by Augustine Coulomb. So this Coulomb's law further can be extended for the force due to multiple charges. Due to multiple charges, what is the force exerted on the test charge? So that is we can find. So I think one example also we have solved with that, and many some of the simple limitations are there, and those also we have seen. And the very important thing after the force is the electric field. So the electric field describe the behavior of a particular charge, how that is described. For instance, we are always giving a point charge, or the charge itself is looking like a spherical shaped. So that is what we have seen. If it is elongated to a line, if it is elongated to a surface, how this field distribution will be, and how the interaction of the uh, two bodies, two charged bodies, which are in different shapes. So that also can be studied by this the field distribution itself. So the very behavior of the field actually describe the charge. So there is no fundamental what you call the procedure available to study the charge as a electron volt or directly is very difficult. But with the field, we can directly get the understanding of a charge, how it is always be. And very important thing we have to note down between the force and the charge is the electric field. Uh, to understand the electric field, we need at least two charges. One is source charge, another one is the test charge. So from the source charge to test charge, we will draw a line joining, and that line joining will give the meaning for the force. But in case of the electric field, such a test charge is not required. In other words, the test charge is everywhere is. So that is the indirect meaning. In that case, what about the field, or what about the platform? How far it is changed with respect to the source charge? So that is described by the uh, electric field intensity. So this is going to behave like a medium between the two charges. So when two positive and negative charges come together, this field lines, they make a linkage, and that linkage makes the force acting on a particular body. So this is very much same as that of the celestial bodies, how they behave. So and one important thing is there is nothing else in between these two bodies. So that is also we have to keep in mind. I've seen some examples. Also, I have given some exercise problem. Kindly work out on that. So now we will move to the same study, that is with the help of Coulomb's law, we have described what about the electric field due to a point charge. So this point charge is very rare phenomena, is often this condition is almost like theoretical one, but we have many applications which are having different shapes. Like if we have a line of charges, assume that in a particular line, so everywhere actually the charge is available, and the charge is defined by with respect to a particular distance. Let's say this is actually 1 meter, and we have huge amount of charges distributed over that. So this can be defined by a new phenomena that is called charge density. So this charge density, if it is a line, then we will mention with rho L. So that is the difference we have to. So in case of point charge, the charge density and the charge both are same. So but in case of this uh, line element, so with respect to a particular line, the charge density is nothing but the charge per unit area or charge per a small area. So we are going to take a very, very small area. And within that, if we calculate the amount of charges, that is nothing but charge density. So how to calculate the total charge density? We can simply integrate that. So when we integrate that, we will get that. So what is a very important thing we have to think in this particular understanding of continuous charges, the DL. So this DL is nothing but the small element or small size of or piece of line we are going to take. And this is tend to be 0. So if it is tend to be 0, then it is almost like infinitely small. And by the way, we are going to equate this with the point charge. And therefore, if it is a point charge or a spherical shaped one, we know that we can apply the Coulomb's law. So if we apply the Coulomb's law for each and every point in this throughout the line, then we can calculate the total electric field out of that. But we have to smartly integrate that. That is what we are going to see in this class. So here everywhere this DL or DS. So the DS also equally meant that it is infinitely small and which almost behave like a point charge. So several point charges are just placed just around the surface and here and there, and these charges are accumulated in such a way that they will be having charge densities. So charge density, again, I am saying that this charge density is nothing but the charge per unit area. Here it is surface one, so it will be like, and depends on the coordinate system, this ds also will change. The next one is the volumetric one. So volumetric one will be having this volume integration with rho v and this dv. So dv, the interesting part is this dl and this dv, or both are almost scalar quantities, where ds is having a plane and there will be a projection in the perpendicular direction. So it is almost like a vector, and therefore the electric field will be in accordance with this surface. So that is the main difference between this three or even four important charge distributions. Now, this charge distributions are, if they are arranged in this way, then how this what do you call the electric field can be calculated. And this is having numerous applications. In fact, the very first application of electromagnetic theory is antenna. So where actually we will take two wires. These two wires are connected with a oscillating current. So a source, and which is connected with positive and negative. Let's say this is positive and negative. So we will be, let's say, having the current is traveling in this way. The same opposite way it will travel. But this will be negative terminal, this will be positive. So now we have to calculate what about the radiated power at this particular point, or the radiated electric field. So we can call that as the electric field. So the easiest way is nothing but if we calculate for a small point location at this, then we will get a small electric field. Then if we integrate this with respect to the length of the case, then we can easily do that. And this is actually we are doing by means of saying a current, but we can make this current. We know that current is nothing but movement of charges at an instantaneous time. This charge is almost freezed, so we can see that the charge distribution is completely different. That is what we are calling it as a rho L. So when we integrate this properly, then we will get the total electric field. So you will see that there will be more several theorems what we are deriving in this. We are having very direct applications in the future, particularly in the communication systems and many important electronic systems. They are having direct systems. Like in the earlier class, I have told about how to print using this concept of the electrostatics, as well as the battery, and there are so many things we can also analyze within the scope of the Coulomb's law related concepts itself. So this three different charged bodies like line and surface and then volume. So if they are available in a space, then how their electric field will be and how to calculate that. So that is what we are going to see now. So first we are going to take electric field due to line charge. So we are going to assume there is a line. Okay, this length of this line is having length L, and this is actually available in the z-axis, and in the z-axis it is available at somewhere else. Let's say this is from z1 to z2. So A point corresponds to 0, 0, z1, and B point corresponds to 0, 0, z2, like that. So this is the line, and this line has the width of 0. So that is what the preliminary or the fundamental assumptions for being a line. Okay, so line will be having only length. There is no width for that. Does not mean that the width is 0. In other words, we can say that there is no there is no variation in the charge distribution over this line, over the width. Like that also we can show. In some of the books, it will be mentioned that the width will be very smaller than length, or this width will be several orders of this length by 50 or length by 100, like that it will be defined. So you should be very careful about this representation. But in case of the fundamental theory or the electromagnetic field theory, we are going to assume this width is 0, so that no problem. So along the xy axis, there is no behavior of charge existing in that particular directions. It is available only in the z direction from A to B point, and this is having a charge distribution of rho L. So the rho L is nothing but charge density. And now what we are going to do, we are going to calculate, we are going to take a arbitrary point in this total length of the line. Let's say 0, 0, z dash. At that particular point, we are going to define a extremely small length of line, often referred as small element. So this dl, you can call it as small element. So this small element has only length of dl, and which is very small. And this dl is going to carry certain amount of charge. Okay, so this rho L. So the total small charge available in this small element. So we often refer this as small charge element. In many of the textbook, particularly the Sadikyu, they have mentioned, sorry, he has mentioned it is a charge element, but in some books it will be mentioned as small charge element. So you can keep any name, but the actual meaning is small. Then only you can go for the large one. So we are going to define there is a small charge available dq, which is nothing but this rho L into dl. This is the total amount of charge available in this total length of dl. And if we can calculate the electric field due to this dl at a distant point, about a distance of r, at arbitrary location, this p, x, y, z, then we can find by changing this x, y, z axis in any direction around the line, then we can easily calculate the total electric field. So first our objective is to define what is this this dE. This DER means it is having projection of this line joining vector R. So then we have to integrate it. So when we integrate that, then we will get the total electric field due to this entire line. We know that the total charge in the line can be calculated by the total integration over the length. We are going to integrate over A to B. So it is very easy. If we know this Z1 and Z2, it is very easy to integrate. And simply nothing but Z2 minus Z1 is the length into this rho L. So that is what going to give this. And since we are integrating, we have to add all of them. That's all. Now we have to calculate the total electric field due to this small current element. So this is so we can say that this dE is nothing but according to Coulomb's law. So what Coulomb's law says that this, so we have to, here there is only we have to accommodate the source charge. The source charge is nothing but this dq into dq by 4 pi epsilon naught r square into this AR vector. So this is the small electric field induced by the small charge. Now this dl can be replaced by rho into dl, and if you integrate on both sides, you will get the total electric field at this particular point due to the entire element. So that is what described here. So the total electric field due to the line element is nothing but integration over the length for rho L dl. So I hope you can easily get that. This is nothing but dl dq 4 pi r square, and AR vector decides this projection of the line which describe the vectorial direction of the field. So you should remember that you have to always write, since it is a equation. So it is very difficult to all the time. It is very difficult to draw this symbol. So you're supposed to do that. Since you are doing with pen, you have to do that. Now what we are going to do, we are going to calculate for a very generalized purpose. So generalized means this point P can be available at any location. This particular point P can be at any location just around that. So if we take a wire, something like that, so any particular point. So you can assume that particular point is described with the circle around that, and to define the height, we can keep the cylinder itself. So that is what you can see. I believe most of you can see that there is a cylinder is described to define this particular point P. So the point P can be available at any particular point. Okay, so this particular point, if it is in the center, then the height of the cylinder you have to vary, that's all. And therefore, in order to calculate for all the field directions, we're supposed to change or convert the vectors from x, y, z axis to the rho and phi and height, that is z axis. So like that, actually, we have to convert that to cylindrical coordinate system. So there is a conversion of this vector is required. So that is what we are going to do first. So first we are actually taking a arbitrary location in the wire, that is 0, 0, z dash. And at that particular point, we are going to take a very small element, that is dl. And this small element, since it is described along the z axis, we are going to take the differential element as dz or dz dash. So here it is available at z dash. It is given as dz dash. You can also keep it as dz. So which describe the change in the change over the z direction. Now we are actually taking this particular point and we are calculating the r vector. So in the rectangle coordinate system, the r vector is very easy. The r vector can be described as this. This is the end point. This is the starting point. So the starting point also we know that, end point also we know that. So x minus 0, x, y minus 0, y, z minus z dash. So now we have to put az vector, ay vector, and az vector, all these unit vectors we have to put, then we will get the r vector. So this r vector is nothing but the line joining vector between this point, this small current, small charge element to the particular point P. And so this r vector, we are going to convert in form of the cylindrical coordinate system. So for that, we have to draw a simple cylinder, and just to at the edge of that top point, the P point should be there. So like that. So we can easily see that from this line, it is available at a radius of r. So that is the radius. So the radius you can calculate easily by this x and y axis, which will give root of x square plus y square. Then it is going to be available at any particular phi. So that is described with the phi, so that we can calculate with the phi equal to tan inverse of this x, sorry, y by x. like that. And along the height direction, so it is going to be available at a particular point. So this particular point is x, y, z. So definitely it's supposed to be at the height of 0, 0, z. So corresponding point can be defined. So now we are going to describe this r vector in form of the cylindrical coordinate system. So for this you have to apply the conversion formula. So when you apply the conversion formula, you will get that. Since along the z direction there is no change, so there won't be since there is phi available in all directions in the same way, so there is no description for phi. So which in other words, p can be available at any phi value. So that is the indirect meaning. So this is how it is defined. So the unit vectors, you're supposed to write them properly. So the r vector is defined in cylindrical form, and then we are calculating the magnitude. So since we are going to take root of, so all the time you need not to take root of. For that you can take r square itself. The benefit is in the later we always use r square, is it, in the expression for Coulomb's law. For electric field we can easily substitute that. So that is the understanding. Now since r vector is available, magnitude of r is available, then one can easily calculate, or one can easily get this ar vector, that is unit vector, we can easily find. Now we have to define again the field expression. So this is what we have seen in the last slide. Now we are going to replace this ar vector and the expression for r square and this dl. The dl become dz vector and this ar vector become this. So how this expression comes up? So this is the r vector, and so up to this. Okay, so this is the magnitude of r, and since this ar vector has one r, so this r square become r cube and divided by √2. So that is what the magnitude form, and this dl become dz dash. That's all. And rho l, 4 pi epsilon naught, all of them are constant. So we are putting outside the integration. So this integration is supposed to be done over the length. The interesting part is this length integration is defined in the xyz direction, but the vector is available in the cylindrical coordinate system. So it is our job to convert this limits also in the same as that of this cylindrical coordinate system. So we supposed to introduce some variable which will describe the cylindrical coordinate systems inside. So how to do that? So for this, the most common method people used to follow is we have to find the location of the P and we have to put a vertical line such that it will go and have a vertical intersection with the Z axis. So once this particular point is very easy to define because it is available X, Y, Z. So obviously this particular point T will be available 0, 0, Z. Okay, so this easily form a triangle. You can see that there are three possible triangles. One is defining with, let's say this is T. So T, A, P. Similarly, T, this arbitrary point Z dash, and P. Similarly, B also. Now, with respect to this line, this PT, and which is having a length of rho, we can easily define in terms of angles. So this particular point P, when it is moving up and down, this alpha will change. And similarly, when it is moving along the horizontal direction, this rho will change. And by the way, we can, and if, when it is moving along the phi direction, of course, the phi itself will change. By the way, we can define the integration also in view of the the cylindrical coordinate system. So how to do that? So here the simple idea is the variable one is z. So when it is moving up and down, we are going to define an angle between this TP line and the line joining vector, that is alpha, which is a variable one. But this alpha can vary from alpha 1 to alpha 2. Always here the alpha 1 is greater than alpha 2. In case if the particular point P is well below the line, we will get just opposite. This alpha 2 will be greater than alpha 1. So at that time, we have to change the vectorial directions. By the way, you can interchange this alpha 1 and alpha 2. So that is very, very easy. So now we got the electric field vector. If you have any doubt, means you can stop at any time. And because you have to derive these expressions in the exams or in the quiz or in the term and examination, you're supposed to do. Anytime if you have doubt, you can stop. And so when you follow it, you will easily, you will also understand, and when you study, it will become very easy. So now we are actually converting this vector with this coordinate systems. So for that, that's alpha is defined. So R vector is defined, which is this value, which is nothing but rho secant alpha. So you can apply this simple trigonometry, you will get that. So the R vector is defined. And similarly, we know that this Z minus Z dash is nothing but this rho tan alpha. So this particular point, this distance is nothing but Z minus Z dash. So this can be defined by rho tan. So by the way, you can isolate the Z dash. So you can rearrange, you will get this equation. Now, since we are converting everything into rho alpha and Z, we are actually going to differentiate that. So when you differentiate this dC dash, then you will get minus rho secant square alpha d alpha. So this we are going to substitute here. And this Z minus Z dash can be replaced by tan alpha easily. So by the way, we can easily substitute all of them. So just we are going to substitute all of them in this expression. So you can clearly see that it is substituted. So this is substituted with rho tan alpha, and this also rho tan alpha will come. But anyway, we know that this is nothing but R square. So this can be replaced by rho secant theta square. By the way, this squares and this 1/2 will be cancelled. You will get only cubic term. And this Z dash, already we know that it is nothing but rho secant square alpha. So that is what it is coming over here. And here these two terms came up with the tan alpha, which is nothing but sine theta by cos theta. This cos theta, when you take out, you will get secant, and that secant and this cubic term cancel. That is why you got this. Finally, anyway, you can cancel out this terms. Only you will get the denominator rho will come, because this is rho square, this is rho. So you will get this one. If you have any doubt, you can stop me. So many people are better than me in terms of mathematics. Kindly stop me and tell what is wrong, something like that. So you should remember this negative term is coming all the way. So this rho L 4 pi, this rho anyway, it is completely independent of this angle. Rho is taken as a constant outside. Now we have to integrate that. So when you integrate, cos become minus sine become cos, and that's all. And these are nothing but corresponding unit vectors, which means that there are two electric field components are available. One is along the rho direction, another one is along the z direction. So that is, I think that is what described here, along the rho direction, along the z direction. This together, or these two vectorial components, ultimately will give the expression for the or final direction of the electric field. So just we have to integrate, and when you integrate and substitute the limits, then you will get the electric field due to a finite line. And finite line of length L, instead of defining the length, it is described between point A to B. And if the length is defined, then you can substitute this in such a way that alpha 1 and alpha 2 can be substituted by triangulating this value. So we already know that. So this is the line. And let's say at a particular point P, we have to calculate, we know the length, and we are going to assume this A is available in 0, 0, 0. By the way, we can say that this is B, B will be 0, 0, length L. So A is here, B is here, and we have to draw the line joining. And this is the T point. We know its length is rho. So now we have to define this alpha 2 and alpha 1. So this simple right angle triangle problem, when you work out based on the dimension. So this dimension, simply it is going to be Z, the location of the P in the Z direction. And this distance we can easily calculate Z minus L. So by doing that, you can calculate alpha 1 and alpha 2, and you can substitute and you can calculate that. If the position of this line is not mentioned, simply it is mentioned as length of the line is L, like that. But if it is clearly mentioned with positions, then the starting point and the end point, if it is known, very well and good, we can easily use this one directly. So this is for the finite length of the line. So this difference in sine square alpha, it clearly indicates that the length increases, then the electric field strength also will keep on increase. Now, if the question comes that if the length of the line is infinite, what will happen? When the length of the line is infinite, okay, so we can, if the particular point is here, origin is here, so no matter whatever the location of the particular point be, we can always assume that is going to be at the almost at the in the plane of the origin itself. So along the XY plane, it is going to be kept, and therefore the let's say we take arbitrarily 2 points, and those 2 points also we are going to take arbitrary point at, let's say, Z1, and this is Z1 dash. Both are available at same distance. So there will be 2 components will be there. One is electric field due to Z, and this is electric field due to Z dash. Both, since they are actually available at the same distance, they will cancel each other. In other words, if you take any particular point along this direction, all the Z component, this Z component will be cancelled, irrespective of whatever may be, if we are considering as an infinite line. And obviously, the electric field will be available only in the perpendicular direction. That is nothing but the E rho vector alone will be available. So that is what it is defined as A rho vector. So which is nothing but the normal vector with respect to the line. So you take a line, infinite line, and the field will be available all the way like this. So only this field component will be available. So in order to calculate the electric field at a particular point, just you have to draw the perpendicular line and calculate the rho at what distance it is available, this particular point. Then what about the charge density? What about the charge density rho L? And by the way, substituting this rho L and rho value, you will get the magnitude. And this rho AR vector, which is nothing but the normal. So this A rho vector, which is nothing but the normal vector. So the normal vector is nothing but along the what direction it is available. If it is available in X, Y, Z axis, you can easily get the normal vector. But if it is available arbitrary direction, let's say like this, if the line is available, then you have to calculate the perpendicular direction. So that is what we are going to see in the next class. We are going to solve few numerical problem where this kind of problem will come. Anybody has idea how to calculate the normal vector for a given line mathematically? So many of you have, I think, attended a JEE and many entrance exam. I believe you will supposed to know that.
So we have to find the cross product for that, for finding the normal vector.
Okay, so between two what? Line vector, we can easily say that. I can easily get the line vector. If I know the line vector.
Vectors of planes, like in the case of planes, we can take the normal vectors of planes and we can then take a cross product of that, and we'll get a normal vector. We'll get another vector, and
Yeah.
the vector which we'll get normal to that vector will be our plane.
Yes. Yeah. So yeah, a very similar method. There is a direct mathematical procedure is available that we will see in the next class. Thank you. So, so um, this is how we have to derive the field expression for any particular arbitrary structure. This is actually for line. Line is a very perfect structure, and many times it is a symmetric structure as well. So for this, the derivation is very simple. When we have, let's say, the vector is like this, when we have a line vector like this, so it is available in X direction as well as Y direction. So you can easily do that. You take, let's say, A, B, and C, 3 points. Then first calculate for A and B, then calculate for C and D. And then you can calculate vectorially, proper vector formula you have to work out. Then when you add the total, then you will get it. So that is the common method. Then we can also find in a loop of wire, if a particular charge density is available, how it will be. And if the charge density we are making as a constant one, but if it is a variable one, let's say from one edge to another edge, it is going like increasing, decreasing manner. The charge densities keep on increasing linearly. After the midway, it is going to decrease. So how to, first of all, we have to describe this rho L. Then we have to bring into the integration. At that time, this rho L cannot be taken out. It's supposed to be part of the integration. So such a problem we will see in the next class. Now there is some alternate method. I found it in another some other books, which is actually a little bit advanced one. Maybe you can think about that. Now what we are going to do, we are going to work for the electric field due to the surface charge. Okay, so line charge we have seen. The line don't have any width, and it is simply having line along the line. The charge is distributed. And similar way, we can also make it for a surface. Here, the surface is defined such a way that the thickness of the surface is 0, and on the surface we have mm, uh, the uh, uh, the charge is distributed in a particular denser manner. So we are going to assume first of all constant or uniform charge distribution. Therefore, it will be given with surface charge density. And so we can easily calculate the total charge which is available over the surface for just by how to integrate that. And if we assume a infinite charge, infinite sheet, okay, because in many places I am saying that for, let's say you take a laptop and it is having a surface, and the laptop has a screen, and this also purely a charged body. And because of that, how the electric field or the flux generally will be formed out of that. So that we can easily find. If we take that surface and you put any particular point anywhere else outside, so they always look like the surface is very bigger than the particular point. Let's say particular point P or something. So this considering this infinite sheet is very much optimum even for many finite structures. If you take antenna and many planar antennas available, so they can also use the very similar expressions in order to find out the simplest form of the electric field. So we are going to get the electric field expression for a infinite sheet charge density has a uniform charge density of rho s. So here we are going to calculate the electric field with respect to the surface. So the surface is given over here, and the surface charge density, and this r is nothing but the distance of the particular point P from the defined surface charge, and this ER vector is the respective line joining vector. So this line joining vector could be possibly having multiple directions, like along the X direction, Y direction, Z direction. 3 directions could be possible that we have to keep in mind. Now the very first job is we have to find the corresponding r vector. So this is with respect to cylindrical coordinate system. So first we are actually defining the this rho. So we are going to take this surface A. The surface A is located at an arbitrary point from the origin point, and this origin point is just kept in such a way that it is just below the desired location, point P. Okay, so point P is located at 0, 0, h at a height. So therefore, this is the origin point, and from the origin point, this A is located. Therefore, this line joining will give us the rho, and this corresponding vector is minus A rho. So minus rho A rho vector. So that is what this, and plus this height. So both we are going to add together, we will get the R vector. So height into AZ vector. So that is what we simply have done here. And this is the magnitude of the R vector R. Same thing when you do for positive side, this rho positive side, you can keep this value positive. There won't be any big difference. Now we are actually defining the surface vector. The surface vector always will be perpendicular to it. And since it is defined with respect to x and y axis, always it is having a normal vector of z vector. And so how to define this area? It is very simple. Rho d rho d phi. So that is the area with respect to the cylindrical coordinate system. And so far now the distribution is, or whether it is square or any shape, it is not mentioned. So we are going to take in this way. So this is the ds. Now we have to substitute all of them. Then we will get vectorial multiplication. Then further we will go for the integration. So this is the electric field, in which we are going to first convert that AR vector. So we know that AR vector is nothing but R vector divided by R. So this R into R square become R cube. That's all. I believe you can easily understand that. Now we have to substitute whatever that is known. So we have known with R vector, and then we know the ds vector. So both we are going to substitute. There are two vectors. This is not vector scalar multiplication. This is actually vector multiplication. So the simplest form of the vector multiplication is dot product. And that is very optimum with respect to the surface potential. And the electric field is also divergent one. So that is why we can easily take the dot product. If it is a magnetic field, then it will be just perpendicular to that. Then we're supposed to go with the cross product. So this ds vector, and this is the r vector, and here you can see r cube is available, and the charge density and the 4 pi epsilon naught taken as a constant, which are kept outside the integration. So we have to integrate over the surface. So how to do that? So we have to integrate, since it is an infinite charge, the rho value, this rho value can be go for the infinite distance, and this phi will be varying from 0 to 2 pi. Like that, actually, we are going to integrate. So this integration, when we do that, you can see that this AZ vector and AZ vector, when you multiply, you will get 1. And this AZ vector and this AR rho vector, when you multiply, you will get 0. So before the integration itself, we can cancel out this A rho component so that the integration becomes simple. And in other words, we can see that with respect to the origin point, if we take a arbitrary point at a distance of rho, let's say minus rho from the origin point, corresponding this rho vector will be available with same mirror of that. If this is having ds, let's say this is ds dash. So both are of same size, located at same place. So this is going to give the electric field, let's say E this is actually with respect to, okay, we will call this is E and this is E, this is E dash and E. Anyway, both the magnitudes are same, but they are actually perpendicular to each other. Therefore, they will cancel each other. So irrespective of whatever the, so which in other words, only you will get this Z means the electric field will be having only projection along the Z direction above. So that is what the ultimate thing. So you will get, this is the remaining component. This is what you have to integrate over the rho 0 to infinite and phi 0 to 2 pi. So I believe you people can easily understand hereafter because you are good at mathematics. So for this integration, the very easiest step is first we have to integrate over 0 to 2 pi because this phi don't have any variable inside. That means with respect to phi, it is always constant. So the easiest way to integrate it, 0 to 2 pi d phi will give 2 pi itself. So that 2 pi has come here. And this h, anyway, it is an independent quantity with respect to d rho. So that also taken out. And this is already here. So this we have to integrate. So the very simplest integration method is nothing but this dp, rho dp will become rho square, d rho square by 2. And this you have to integrate. So when you integrate that, you will get 1 by rho square. So this actually, I think this will come rho square plus h square whole power minus 3 by 2. So when you differentiate that, all these things will come with respect to rho square. So you have to substitute for 0 to infinite. When you substitute 0 to infinite, when you substitute 0, you will get h square root. So which will become h. So you will get the first, when you substitute this rho equal to 0, you will get h term. And then, sorry, 1 by h will come. And then second term minus infinite. When you apply infinite, then you will get 1 by of infinite 0 will come. So simply you will get 0. So the resulting value is 1 by h. So this, the integration result 1 by h, 1 by h, and this h will be cancelled. So you will get finally this term. So ES, that the electric field due to a infinite surface charge, it is simply rho s by 2 epsilon naught. The very important thing we have to remember here is the h finally cancelled out. So the particular point P at any particular height, it is always going to get this particular magnitude, irrespective of whatever the distance. So this is very, very interesting factor. So if you have, let's say, a very, very big sheet charge density and very big, like let's say, like a 10 cross 10 size and a small rubber ball size or like tennis ball size charge you are going to keep just about that, then the force exerted will be always in the perpendicular direction. So this is very easiest method to make the particular charged body in a particular location itself. So by this way, we can easily do that. So, and this is actually available in XYZ direction. So you can easily say that the normal vector is AZ vector. So you can easily do that. But if this sheet is available or arbitrarily located, it is located somewhere else. With respect to the XYZ direction, it is located in a particular direction. Then it is safer to define this. So we can easily say that the electric field due to infinite sheet charge is going to be purely depends on the charge distribution. And this charge distribution divided by 2 epsilon. So material property sometimes will come and play the role of the electric field. And interestingly, the electric field, this particular point P, when you bring it just below it, then you will get minus term will come. Okay, so but however, there also it is still perpendicular. In other words, along the sheet charge, along this direction, along this direction, along this sheet direction, along the plane of the sheet charge, there is no electric field component available. So the electric field will be always be perpendicular. It is very difficult even to draw it. This is this is one of the very common practice people used to follow when they calculate for very big size of charged bodies. Like if you take a ship and it is very, very big and it is, let's say it is charged, then the electric field definitely will be perpendicular to the surface of it. And so that component alone, it is enough to study to get most of the information about the shape of the device, shape of the ship or aeroplane or such a very big bodies. Here is another example that we are going to assume a finite sheet. This finite sheet is spreaded from 0 to 1 and 1. So along the X and Y direction. So this is actually, we can take, this is X axis, this is Y axis, this is Z axis. So exactly 0 to 1 and 0 to 1, like that it is defined. So this is the sheet charge, and this is having a sheet charge density is not uniform. It is varying with respect to X and Y axis. Okay. And at a particular point P, this P is available at 0, 0, 5. So we have to calculate the total electric field at this particular point. So how to do that? So it is at the corner. You can easily say that it is not even at the center. So this is actually the solution is given here. We will, along with the numerical problems, we will work out this way. We will see how to calculate this electric field. Let me skip for now, but in the next class, we will solve at least 4 or 5 numerical problems. Don't skip that class. And in case of volume charge, the very similar workout, but it will be very tricky since it is a cylindrical one. It is not because of the coordinate system. It is because of the so-called the intrinsic nature, since it is having theta and phi. So there are several variables will come inside. That makes the derivation a little bit more tricky. So if other two charges, line charge and surface charge, if it takes 1 page, this will take 1.5 page. So that's the difference. But anyhow, the interesting thing is the final result of the electric field will be always perpendicular direction. So if you take a volume, a spherical one, you will always get the electric field in the perpendicular direction. This is what the Coulomb's law also says that. So you can see very similar that of the Coulomb's law, it is available here. And so this is nothing but the source charge density. And so we know that the Q divided by 4 pi r square and this AR vector. So which is nothing but the electric field. For this Coulomb's law, this is the field from the volume charge. So there is no big difference, but anyhow, we will see. I'm leaving this to you. You can read by yourself. Since it is an open book test, you're supposed to learn all the things. Well, so I'm stopping the class now here. In the next class, we will see at least some 4 numerical problems. If you have any questions, feel free to ask.